This is an example of a 2D stack. In this video, you will learn how to handle multiple clearances and angular rotations. As you see here, the green interface has a much better position fit with the same tolerances. But let's start by looking at the simple tolerance stack with 3 boxes and how single interfaces can create the need for 2D stacks. This is a 1D stack. We'll use this case to explain the differences between 1D, 2D, and 3D stacks. We might want to change one of the boxes to a cylinder, and in the shown example, it does not really change our tolerance stack. The cylinder's width is given by its diameter, instead of a length between 2 opposing planes. But this depends on the size of the cylinder and the height of the boxes. This changes where the boxes interface with the cylinder, and we see that the width will vary with the height of the boxes, adding complexity. Therefore, we will need to know the width of the cylinder at a given height to evaluate this tolerance stack. We know the height of the triangle is the difference in radius and height of the purple box. Using Pythagoras, we can find the missing piece in our triangle. We can reuse this expression for the second part of the cylinder, and we now know the trigonometric expression for our tolerance stack. Together, let's try to create this tolerance using iterations on the RD8 platform. First, we upload the new step file before the RD8 platform analyzes the geometry. The system has already automatically recognized these parts, and we can check the matches here if needed. We then need to tell the platform which parts have been replaced, if it cannot tell from the naming. In this case, we will match the yellow box with the cylinder. Let's jump to our calculations overview and create the new stack. And of course, give it a name. We'll insert the illustration supporting our calculation by directly copying it from PowerPoint. This makes it easy for our colleague to review the stack later. We'll then toggle 3D to insert a screenshot view of our model. Now let's insert the leader lines one by one, starting with our point of interest. We'll now draw up each of the parameters while giving each a unique designation. We will finish off with adding the lines and arrows for height and diameter parameters. For these parameters that do not follow the primary stack direction, hold down Shift to unlock the line snapping. They get a subscript to show that they are related to the box A and box B. Now we can assign each parameters an element with a corresponding parameter with a nominal and tolerance values. We can reuse from our previous iteration, but we need to define the diameter for the yellow box, as well as the height for the 2 square boxes. Remember to select your calculation method and set your targets. Let's write out our calculation formula. A and B both work in negative direction. For the width of the cylinder, we'll need the expression from our supporting illustration. The first term inside the square root is the radius, or half the diameter, parameter D, while the second term is the difference between the radius and height of the box. The height adds the extra dimension to our stack, making it 2-dimensional. We'll copy the term for the second part of the cylinder, and finally parameter E. Our stack still passes with the 1 million trials from the Monte Carlo simulation. Notice that more than 15% of our variation are impacted by the height of the boxes. Let's say the boxes are molded with draft angles in the interfacing surfaces. The added variance across the depth makes the stack become 3-dimensional. 3D stacks are complex to handle and close to impossible to review and verify. Complex tools like 3DCS and CETL are needed for 3-dimensional stacks. However, most stacks can be handled in 2D, especially if applying robust design principles. How can you apply robust design principles here? Consider whether you can avoid non-perpendicular contacts, and design interfaces that are easy to define. For example, on a drafted surface, create a non-drafted section of that surface as your well-defined interface. Let us dive back in a 2D stack. In this case, an example with well-defined interfaces, a pull-out drawer. This is a classic dogbone configuration, with a set of wheels as Y constraints at the front, while the back wheels constrain the rotation of the drawer inside the frame. This allows for angular misalignment of the drawer, which could create interference with neighboring drawers or lead to other poor user experiences. We can check that by creating a tolerance stack, which evaluates the clearance in Y direction between the edge of drawer front and side of the frame. The stack basically comprises of two separate stacks, the clearance at the front wheels and the clearance at the back wheels. However, due to the distance from the front wheel to the drawer front, the stack will also include elements in the X direction. Hence, it is a 2D stack. As with many 2D tolerance stacks, it is a matter of triangles. In this case, two similar triangles, with same angles, but the sides in proportion. We simply multiply the sum of clearances with the ratio between the triangles. Now let's jump to the RD8 platform to set up the tolerance stack. We have already checked that the fit at the front wheels never has interference, as well as no interference at the back wheels. I have cheated a bit here and already set up the illustration and assigned the parameters. We are ready to set up the formula. The illustration on the right has the parameters E and A2 from the 1D stack with no angular contribution. The A parameters are similar to the fit at the front wheels, while the B parameters are similar to the fit at the back wheels. First, we add the parameters from the simple 1D stack, A2 subtracted by E. Then add the clearance from each of the wheels, which both overall work in a negative direction for our point of interest. Beware, the result of the parenthesis should therefore be positive. The fourth term is the clearance at the back wheels using all the B parameters. Notice that all terms are divided by 2, as we only need half of the total clearance. We will group the two clearances as one term, so that we can add the ratio between the smaller and larger triangle, where both sides comprise of 2 parameters each. In this example, the numerator is the larger triangle comprising the sum of C1 and D1, while the denominator is the smaller triangle. We see that the stack is failing our lower specification limit that ensures the drawer does not hit neighboring drawers. It may be apparent to you that this is not the worst-case state. When pulling out the drawer, the triangles change, and especially the proportion between the sides. To ensure the function of our drawer, we will also create a stack in the out state. Again, I have cheated a bit and already created the stack using a screenshot from our CAD software to show the out state. The building blocks are similar, with only parameters in the smaller triangle changing. This triangle now includes 3 parameters, C1 through C3. Again, the stack fails our lower specification limit of 0. So we will need to do something to ensure the function of our drawer. We can optimize the 2 fits and evaluate whether this is enough for the 2 stacks to pass. Additional clearance can be removed at the front wheels, which is actually enough for the in-state stack to pass. Optimizing the clearance at the back wheels is not enough for the out-state stack to also pass. So in this case, we would need to redesign our drawer front. For example, by including spring-loaded wheels, which removes all clearances. In the example from the introduction, you can see the difference in performance between 2 different designs. The only difference is the distance between the constraints. Same clearances. So remember how proportions in 2D stacks can work to your advantage. Your design has the potential to be more precise without tightening tolerances and increasing cost. Another example interface would be this slotted connection between 2 cylinders. The angular movement of the orange cylinder is again a 2-dimensional application of trigonometry. Adding additional parts, for example this purple part, to the stack is just a matter of adding the contribution from that interface clearance to your existing stack. So to sum up, you may encounter 2D stacks due to 2 main reasons: angular offsets from clearances or non-parallel interfaces. The latter, we generally try to avoid to make our design clear and limit the amount of parameters needed in design control. This also helps both you and your colleagues with reviewing stacks, just like supporting illustrations are more than welcomed.
Do you know the quality of your designs? We do.